Hello there, and welcome to Midnight Science. I'm so glad you found your way here tonight. Maybe you've been curious about the invisible universe, or maybe you just need somewhere calm to rest your thoughts. Either way, you're in the right place. Tonight, we're going to drift through one of the cosmos' deepest mysteries, dark matter, the substance that holds galaxies together, that shapes the universe itself, and yet remains completely invisible to our eyes. There's nothing you need to do right now. Just let yourself settle. Let the day fall away like autumn leaves. Let your breathing slow and your mind grow soft. We'll move gently from idea to idea, exploring the hidden scaffolding of reality, the invisible threads that connect everything we can see. Some of what you hear might surprise you. Other facts might simply wash over you like waves on a quiet shore. And if these peaceful explorations help you rest, feel free to like and subscribe. It helps others find this place of calm, one sleepy soul at a time. Now, if you're ready, let's begin our slow drift through the invisible universe. Dark matter makes up most of the universe's mass. When you look up at the night sky, you're seeing only a fraction of what's really there. All the stars, all the planets, all the gas and dust, everything that glows or reflects light, makes up less than 5% of the universe's total mass and energy. The rest is hidden. About 27% is dark matter, a form of matter that doesn't interact with light at all. It doesn't shine, doesn't reflect, doesn't absorb. It's simply there, invisible and silent, holding the cosmos together with its gravity alone. The remaining 68% is dark energy, even stranger still. But tonight, we're focused on dark matter, that quiet presence woven throughout space. Most of what exists cannot be seen. And yet, without it, galaxies would fly apart, stars would never have formed, and we would not be here to wonder about it. We can only detect dark matter through gravity. Dark matter is shy. It doesn't want to be seen, touched, or measured directly. It passes through ordinary matter like a ghost through a wall. No light bounces off it. No heat radiates from it. So how do we know it's there? Through its gravitational pull. When astronomers watch galaxies spin, they notice something strange. The outer stars move much faster than they should, given the visible mass of the galaxy. According to the laws of physics, those stars should be flung out into space. But they're not. Something invisible is holding them in place, adding mass we cannot see. That something is dark matter. We detect it not by looking at it, but by watching how it shapes the things we can see. It bends light from distant galaxies. It holds clusters together. It leaves fingerprints in the fabric of space itself. Dark matter may be made of particles we've never discovered. What is dark matter made of? We don't know. Scientists have spent decades searching for the answer, and it remains one of the greatest mysteries in physics. The leading theory suggests that dark matter is composed of particles, but not the kind we're familiar with. These hypothetical particles don't interact with the electromagnetic force, which is why they don't produce or interact with light. Some candidates have names like WIMPs, weakly interacting massive particles, or axions, incredibly light and elusive. Others propose more exotic ideas, particles from dimensions beyond our own, or remnants from the universe's earliest moments. Experiments deep underground, shielded from cosmic rays, wait in silence for a dark matter particle to collide with ordinary atoms. So far, the results have been whispers, hints, but nothing definitive. The universe keeps its secret close. Galaxies rotate like solid disks because of dark matter. Imagine a merry-go-round. The horses near the center move slowly. The ones on the outside move quickly to keep up. That's how planets orbit the sun. The farther out, the slower they move. But galaxies don't behave that way. When astronomers measured the rotation speeds of stars at different distances from a galaxy's center, they found something unexpected. Stars on the outer edges moved just as fast as those closer in. It was as if the galaxy rotated like a solid disk, not a collection of independent stars. This was impossible unless there was much more mass than we could see. That invisible mass, spread in a vast halo around each galaxy, is dark matter. It doesn't glow, but it holds. And in its grip, galaxies spin in ways that defy what we see with our eyes alone. Dark matter was first proposed to explain missing mass. The story of dark matter begins in the 1930s with a Swiss astronomer named Fritz Zwicky. He was studying the Coma Cluster, a group of over 1,000 galaxies bound together by gravity. Zwicky measured how fast these galaxies were moving and calculated how much mass would be needed to hold the cluster together. The numbers didn't add up. The galaxies were moving so quickly that the cluster should have torn itself apart long ago. But it hadn't. Zwicky proposed a radical idea. There must be unseen mass, what he called dark matter, holding everything in place. At the time, most astronomers dismissed the idea. Decades later, in the 1970s, astronomer Vera Rubin confirmed similar findings by studying the rotation of individual galaxies. Her meticulous work provided strong evidence that Zwicky had been right. The universe was full of something we couldn't see. Dark matter doesn't clump like ordinary matter. Ordinary matter, the stuff of stars and planets and people, clumps together. It forms dense structures because atoms collide, lose energy, and settle. But dark matter behaves differently. It doesn't collide in the same way. It passes through itself and through ordinary matter almost without interaction. Because of this, dark matter forms large, diffuse halos around galaxies rather than collapsing into dense cores. These halos are smooth and extended, like invisible fog wrapping around the bright, visible parts of galaxies. In computer simulations of the universe, dark matter forms a vast cosmic web, long filaments stretching across billions of light years. Galaxies form where these filaments intersect, like beads on invisible strings. Dark matter provides the framework, and ordinary matter fills in the details, lighting up the structure from within. The Milky Way sits inside a dark matter halo. Our galaxy, the Milky Way, is not just a disk of stars and gas. It's wrapped in something much larger, a halo of dark matter that extends far beyond the visible edge. This halo is roughly spherical and contains several times more mass than all the stars, planets, and gas in the galaxy combined. As the Earth orbits the Sun, and the Sun orbits the galactic center, we're also moving through this dark matter halo. Trillions of dark matter particles pass through you every second, completely unnoticed. They don't interact with your atoms or leave any trace. But they're there, part of the invisible architecture that holds the Milky Way together. In a way, we live inside dark matter, moving through it like fish through water, never feeling its presence, but shaped by its gravity all the same. Dark matter may interact with itself in unexpected ways. Most models of dark matter assume it's completely inert. interacting only through gravity. But some physicists wonder if dark matter might have its own hidden forces, a dark version of electromagnetism, or other interactions we haven't yet discovered. If so, dark matter particles could collide, annihilate, or even form dark atoms and dark molecules. There could be an entire dark sector of physics, a parallel universe of particles and forces, invisible to us but rich with complexity. Some observations hint at this possibility. Certain galaxy clusters show signs that dark matter might scatter or slow down during collisions, behavior that simple non-interacting particles wouldn't display. These ideas are speculative, but they open the door to a deeper mystery. What if dark matter isn't just one thing, but a whole hidden world coexisting with ours, just out of reach? Dark matter helped the first galaxies form. In the earliest moments after the Big Bang, the universe was a hot, dense fog of particles and radiation. As it expanded and cooled, tiny fluctuations in density began to grow. Gravity pulled matter toward the densest regions, but ordinary matter couldn't collapse efficiently at first. It was still too hot and too influenced by radiation pressure. Dark matter, however, was different. It didn't interact with light or radiation, so it could start collapsing earlier. Dark matter formed the first gravitational wells, deep pits in the fabric of space where ordinary matter could eventually gather. Without dark matter, those early structures would have taken much longer to form, if they formed at all. The first stars and galaxies emerged within halos of dark matter, lighting up the darkness from within these invisible cradles. In a very real sense, dark matter was the midwife to the visible universe. Some scientists think dark matter could be primordial black holes. Not all theories of dark matter involve exotic particles. One alternative idea suggests that dark matter might be made of black holes, specifically primordial black holes that formed in the chaotic conditions just after the Big Bang. These wouldn't be the black holes left behind by dying stars. Instead, they would have formed from tiny regions where matter was compressed so intensely that it collapsed directly into black holes. These objects could range in size from smaller than an atom to many times the mass of the Sun. If they exist in large enough numbers, they could account for some or all of the dark matter we observe. Searches for primordial black holes have looked for telltale signs like gravitational lensing or the ripples they'd make in space, but so far, no definitive evidence has been found. Still, the idea lingers, a reminder that the universe's mysteries might have simpler, stranger explanations than we expect. Dark matter might decay very slowly over time. Most models assume dark matter is stable, unchanging over billions of years. But what if it isn't? Some theories propose that dark matter particles might decay very slowly into lighter particles or radiation. If this is true, we might be able to detect the faint glow of dark matter decay in distant galaxies or in the space between them. Astronomers have searched for unusual X-ray signals or gamma rays that could be signs of decaying dark matter. A few anomalies have been found. Faint signals that don't quite match known sources, but nothing conclusive. If dark matter does decay, it would mean the universe is slowly changing, the invisible scaffolding gradually dissolving over eons. But the process would be so gradual that it wouldn't threaten the structure of galaxies or the cosmos for trillions of years. just a quiet transformation happening in the background of time. We might be swimming through a river of dark matter. The sun doesn't sit still. It's orbiting the center of the Milky Way at about 220 kilometers per second. And as it moves, it carries the Earth and all the planets with it. As we travel through the galaxy, we're also moving through the dark matter halo that surrounds it. But dark matter isn't spread evenly. It's clumpy, with streams and currents flowing in different directions. Some of these streams might be the remnants of smaller galaxies that were torn apart and absorbed by the Milky Way long ago. Their dark matter still follows its original path, creating rivers of invisible matter flowing through our neighborhood. At any given moment, we might be passing through one of these streams, and the density of dark matter around us could be higher or lower than average. Experiments designed to detect dark matter particles are sensitive to these variations. A change in the dark matter wind could make the difference between detection and silence. Dark matter may have temperature, just not one we can feel. When we think of temperature, we think of heat, the motion of atoms bouncing and vibrating. Dark matter doesn't work that way. It doesn't emit heat or light, but it can still have a kind of temperature related to how fast its particles are moving. In the early universe, dark matter was hot, meaning its particles moved quickly, zipping across vast distances. As the universe expanded and cooled, dark matter slowed down, becoming cold. Today, dark matter is thought to be cold, moving relatively slowly compared to the speed of light. This coldness is one reason it could clump together to form the halos around galaxies. If dark matter were still hot, it would be too energetic to settle into structures. There's also the idea of warm dark matter, a middle ground where particles move a bit faster, creating slightly different cosmic structures. The temperature of dark matter, though invisible, shapes the universe we see. Dark matter could be hiding in extra dimensions. Our universe has 3 dimensions of space and 1 of time, or so it seems. But some theories in physics suggest there could be additional dimensions, tiny, curled up, and hidden from our perception. If these extra dimensions exist, dark matter might live there, or at least partially. It could be a particle that extends into dimensions we can't access, which would explain why it interacts so weakly with ordinary matter. In this view, dark matter is all around us, but most of its existence is folded away in directions we can't see or move through. Gravity, however, can reach into these extra dimensions, which is why we feel dark matter's gravitational pull, even if we can't touch it or see it. These ideas come from string theory and other advanced frameworks, and they're far from proven. But they offer a glimpse of how strange and layered reality might truly be. The cosmic web is built on dark matter. If you could see the universe on the largest scales, you'd witness something breathtaking. Galaxies aren't scattered randomly. They're arranged in a vast web of filaments, clusters, and voids, a cosmic tapestry stretching across billions of light years. This structure, called the cosmic web, is built on dark matter. Dark matter formed the filaments first, drawn together by gravity in the early universe. Ordinary matter then flowed along these invisible threads, gathering in the densest regions and lighting up as galaxies and stars. The voids, enormous empty regions between the filaments, contain very little matter of any kind. The cosmic web is a map of dark matter's influence, a blueprint drawn in gravity and time. And we live somewhere along one of those threads, a tiny glowing point in a structure that spans the observable universe. Dark matter might explain why galaxies have flat rotation curves. This is one of the most compelling pieces of evidence for dark matter. When astronomers measure how far stars orbit the center of a galaxy, they create what's called a rotation curve, a graph showing speed versus distance. For our solar system, planets farther from the sun move slower, a result of gravity weakening with distance. Galaxies should behave the same way, with outer stars moving more slowly, but they don't. Instead, the rotation curve stays flat. Stars at the edge of a galaxy move just as fast as those closer in. This is only possible if there's a large amount of unseen mass, dark matter, extending far beyond the visible disk. The dark matter halo provides the extra gravity needed to keep those outer stars moving quickly. Without it, galaxies would look and behave very differently, and the universe would be a stranger, less structured place. Dark matter doesn't emit or absorb electromagnetic radiation. Light is part of the electromagnetic spectrum, and so are radio waves, microwaves, X-rays and gamma rays. All these forms of radiation are carried by photons, particles that interact with charged particles like electrons and protons. But dark matter doesn't carry any electric charge. It doesn't interact with photons at all. That's why it's dark. You can't see it with your eyes, detect it with a telescope, or heat it with a laser. It doesn't glow in the infrared or flash in the ultraviolet. It's electromagnetically invisible. This makes dark matter incredibly difficult to study. We can't shine a light on it or bounce a signal off it. All we have is gravity, the one force that dark matter does respond to. And through gravity, through the bending of light and the motion of galaxies, we trace its presence like a shadow cast by something we cannot see. Dark matter was essential for the formation of structure in the universe. Without dark matter, the universe would be a very boring place. After the Big Bang, matter was spread out almost uniformly, with only tiny variations in density. These variations were the seeds of all future structure, but they were so small that ordinary matter alone couldn't amplify them quickly enough. Radiation pressure and other forces resisted collapse. Dark matter, immune to these pressures, began clumping together much earlier. Its gravity pulled ordinary matter into the growing wells, and over time, these regions became the first stars, galaxies, and clusters. Computer simulations show that without dark matter, the universe would be a vast, nearly empty expanse with very few galaxies, certainly none like the Milky Way. Dark matter didn't just help build the universe. It made the universe we live in possible, a cosmos rich with stars, planets, and life. Dark matter halos can collide and pass through each other. When two galaxies collide, it's a slow, majestic event that unfolds over millions of years. The stars usually pass by each other without touching. Space is vast, and stars are small. But the dark matter halos surrounding those galaxies also interact, or rather, they don't. Because dark matter doesn't collide with itself in the way ordinary matter does. The two halos can pass right through each other, barely slowing down. Astronomers have observed this in colliding galaxy clusters, most famously in the Bullet cluster. In this system, the visible gas from the two clusters collided and heated up, glowing in X-rays and slowing down. But the dark matter, detected through gravitational lensing, kept moving, passing through the collision almost untouched. This behavior is exactly what we'd expect if dark matter is made of weakly interacting particles. It's one of the strongest pieces of evidence that dark matter is real and distinct from ordinary matter. Dark matter particles might be passing through you right now, at this very moment, as you rest and listen. Countless dark matter particles are streaming through your body. They enter from one side and exit from the other without leaving a trace, without touching a single atom. You don't feel them. They don't slow down or speed up. They simply pass, like photons through a clear window. The density of dark matter in our region of the galaxy is very low, far less dense than air, or even the best vacuum we can create in a lab. But the particles are numerous, and they're always moving. Some estimates suggest that thousands, even millions, of dark matter particles pass through every square centimeter of your body every second. Despite this constant flow, no interaction has ever been directly detected. Dark matter is the ultimate ghost, present everywhere, touching nothing, shaping everything from afar. Scientists use underground detectors to search for dark matter deep beneath mountains. Shielded from cosmic rays and radiation, scientists have built some of the most sensitive instruments on Earth. These detectors are designed to catch the faintest whisper of a dark matter particle colliding with an ordinary atom. The detectors are kept in underground labs to block out interference from other particles that constantly rain down from space. Inside tanks of ultra-pure liquids or crystals cool to near absolute zero weight in silence. If a dark matter particle happens to strike a nucleus, it might produce a tiny flash of light or a minuscule vibration. The challenge is enormous. Dark matter interacts so rarely that you might need to wait years for a single event. And even then, it's hard to distinguish from background noise. Many experiments have run for decades without a definitive detection. But the search continues. Patient, meticulous, and hopeful. Somewhere in the dark, the universe might finally whisper back. The amount of dark matter in the universe is precisely measured. Although we can't see dark matter directly, we know how much of it there is with surprising precision. Observations of the cosmic microwave background, the ancient light from the early universe, provide a detailed snapshot of the cosmos when it was just 380,000 years old. The patterns in that light, tiny fluctuations in temperature, reveal the balance of different kinds of matter and energy. From this, scientists have determined that dark matter makes up about 27% of the universe's total mass energy content. Ordinary matter, everything we can see and touch, accounts for only about 5%. The rest, roughly 68%, is dark energy, a separate mystery. These numbers have been confirmed by multiple independent methods, from galaxy surveys to the motions of galaxy clusters. The measurements agree to within a few percent. We may not know what dark matter is, but we know how much of it there is, and that knowledge itself is a quiet triumph of modern science. Dark matter might have played a role in the formation of supermassive black holes. At the center of most large galaxies, including our own Milky Way, lies a supermassive black hole. These objects contain millions or even billions of times the mass of the Sun, and we're still not entirely sure how they formed. One theory suggests that dark matter played a crucial role. In the early universe, dark matter could have collapsed into dense clumps, creating deep gravitational wells. ordinary matter would then fall into these wells, accumulating rapidly and forming the seeds of supermassive black holes. Dark matter might have also slowed the growth of these black holes in predictable ways, or even been captured and accumulated around them, adding to their mass. Some models suggest that the presence of dark matter affects how black holes merge and grow over time. The connection is still being explored, but it's possible that the invisible scaffolding of dark matter shaped not only galaxies, but the monsters at their hearts. Dark matter doesn't clump as tightly as stars or planets. Ordinary matter can lose energy through radiation, cooling down and collapsing into dense objects like stars, planets, or even you. But dark matter can't radiate energy away. It doesn't have a way to shed the energy of motion and settle into convex structures. This means that while dark matter forms halos around galaxies, it remains diffuse, spread out over enormous volumes. Even in the densest regions, like the center of a galaxy, dark matter is far less concentrated than the stars and gas. It's more like a fog than a solid. This difference is important. It means that dark matter provides a smooth gravitational background, a kind of invisible cushion that ordinary matter rests upon. The bright, compact structures we see, stars, planets, galaxies, are outliers, rare islands of density in a universe dominated by the faint and the spread out. Some theories propose dark matter is made of axions. Among the many candidates for dark matter, one of the most intriguing is the axion. Axions are hypothetical particles, incredibly light and incredibly numerous. If they exist, they were produced in vast quantities in the early universe, and they could still be all around us today. Unlike heavier dark matter candidates like WIMPs, axions would form a kind of quantum wave permeating space, oscillating at specific frequencies. Scientists are building experiments to detect these oscillations, using devices that resemble sensitive radio receivers. If an axion wave passes through the detector and its frequency matches the tuning, it could produce a faint signal. The search is painstaking, requiring exquisite precision and patience. But if axions are real, they would not only solve the dark matter mystery, they would also resolve other puzzles in particle physics. For now, the axion remains a ghost in the equations, tantalizing but unproven. Dark matter could have its own complex particle zoo. When we look at ordinary matter, we find a rich diversity of particles: quarks, leptons, photons, gluons, each with different properties and roles. What if dark matter is equally complex? Some physicists propose that the dark sector, the realm of dark matter, could have its own periodic table, its own forces and interactions invisible to us. There could be dark photons, dark electrons, even dark atoms and dark molecules. If this is true, there might be entire dark structures out there, dark planets, dark stars, or dark life, all completely undetectable except through gravity. This idea is highly speculative, but it challenges the assumption that dark matter is simple and boring. The universe might be far stranger than we imagine, filled not just with invisible matter, but with a hidden cosmos running parallel to our own, silent and unseen. Dark matter distributions can be mapped using gravitational lensing. Though dark matter is invisible, we can map where it is by watching how it bends light. This technique, called gravitational lensing, relies on Einstein's insight that mass warps space, and light follows the curves of that warped space. When light from a distant galaxy passes through a region filled with dark matter, its path bends. The galaxy appears distorted, stretched into arcs or even rings. By carefully analyzing these distortions, astronomers can reconstruct the distribution of dark matter in the foreground. This method has been used to map dark matter in galaxy clusters, revealing the invisible halos and filaments that hold the clusters together. In some cases, the maps show that dark matter is more spread out than the visible galaxies, confirming that it forms large, diffuse structures. Gravitational lensing turns dark matter into a visible artist, painting its presence in the curves and smudges of distant light. Dark matter might affect the orbits of objects in our solar system. Most discussions of dark matter focus on galaxies and the cosmos, but some scientists have wondered whether dark matter could have subtle effects much closer to home. If the solar system is passing through a dense stream or clump of dark matter, could it influence the orbits of planets, asteroids, or comets? The effect would be incredibly small, far too tiny to notice in everyday observations. But over long timescales, or with extremely precise measurements, it might leave a trace. Some researchers have looked for anomalies in the orbits of outer solar system objects or the motions of spacecraft, searching for signs of dark matter's gravitational tug. So far, no definitive evidence has been found, but the idea remains intriguing. Dark matter is everywhere, even here in our quiet corner of the galaxy, and it's possible that with the right tools, we might detect its presence not in distant galaxies, but in our own cosmic backyard. Dark matter may help explain the universe's large-scale structure. Look at a map of the universe on the grandest scales, and you'll see galaxies arranged in filaments and sheets, with vast voids in between. This cosmic web is not random. It's the result of billions of years of gravitational evolution, shaped primarily by dark matter. In the early universe, tiny fluctuations in density were amplified by gravity. Dark matter collapsed first, forming the skeleton of the web. Ordinary matter followed, flowing into the dark matter halos and lighting them up with stars and galaxies. Simulations that include dark matter reproduce this structure remarkably well, matching what we observe in deep sky surveys. Simulations without dark matter fail. The structures form too slowly, or not at all, or they look wrong. This agreement between simulation and observation is one of the strongest arguments for dark matter's existence. It's not just a quirk of one galaxy or cluster. It's a fundamental part of the universe's architecture. Some scientists search for dark matter by looking for its annihilation. If dark matter particles are their own antiparticles, they could annihilate when they meet, producing a burst of energy in the form of photons or other particles. This process would be rare, but in regions where dark matter is dense, like the centers of galaxies or the sun, it might happen often enough to detect. Astronomers search for excess gamma rays or other signals coming from these regions, looking for signs of dark matter annihilation. Some studies have found anomalies, faint glows, or unexpected particle signatures, but these could also be explained by other astrophysical processes. The challenge is distinguishing the signal of dark matter from the noise of the cosmos. Still, the search continues. If dark matter does annihilate, even occasionally, it would offer a direct window into its properties, a rare moment when the invisible becomes visible. if only for an instant. Dark matter doesn't experience friction. When ordinary matter moves through a medium, like air or water, it experiences friction. It slows down, heats up, and loses energy. Dark matter doesn't do that. It doesn't collide with other particles in the way ordinary matter does, so it doesn't experience friction or drag. This has important consequences. When galaxies collide, the visible gas clouds slam into each other, slow down, and heat up, glowing brightly in X-rays. But the dark matter halos pass through each other almost unaffected, like two clouds of smoke drifting through one another. This behavior helps us understand what dark matter is, and perhaps more importantly, what it isn't. It's not made of ordinary atoms, and it doesn't interact through the electromagnetic or strong nuclear forces. It moves through the universe smoothly, silently, shaped only by gravity's gentle hand. Dark matter might form dark stars in the early universe. In the very early universe, before the first ordinary stars ignited, there may have been another kind of star. Dark stars. These hypothetical objects would have formed when dark matter particles, accumulating in dense regions, began to annihilate. The energy from these annihilations could have heated the surrounding gas, creating a glowing cloud supported not by nuclear fusion, but by dark matter interactions. Dark stars would have been huge, perhaps thousands of times more massive than the Sun, and they would have shone with a cool, diffuse light. They wouldn't have lasted long. Eventually, they would have collapsed to form black holes or triggered the formation of ordinary stars. We've never detected a dark star, and we may never know if they existed. But the idea is captivating, a reminder that the early universe might have been populated by objects utterly unlike anything we see today. Fleeting giants powered by the invisible. Dark matter provides the gravity to hold galaxy clusters together. Galaxy clusters are the largest bound structures in the universe, containing hundreds or even thousands of galaxies, along with vast amounts of hot gas and dark matter. The galaxies in a cluster move at incredible speeds, hundreds or thousands of kilometers per second. According to the laws of gravity, if you add up all the visible mass in a cluster, the stars and gas, there's not nearly enough to hold it together. The galaxies should fly apart, and the cluster should dissolve, but they don't. The secret is dark matter. It makes up the majority of the cluster's mass, providing the gravitational glue that binds everything together. Observations show that dark matter in clusters is distributed in large, smooth halos that extend far beyond the visible galaxies. This dark matter is essential not just for individual galaxies, but for the largest structures in the cosmos. The density of dark matter in the Milky Way is very low. Though dark matter dominates the mass of the Milky Way, its density in our neighborhood is surprisingly low. Near the Sun's location, the density of dark matter is roughly 1 proton's worth of mass per cubic centimeter. That might sound like a lot, but it's far less dense than the best vacuum we can create in a laboratory. In fact, it's far less dense than the interstellar medium, the sparse gas between stars. Despite this low density, the sheer volume of the dark matter halo means it contains far more mass than all the stars in the galaxy combined. It's spread so thin that you'd never notice it on human scales. But over cosmic distances, over billions of years, that faint, diffuse presence accumulates into the dominant force shaping the galaxy's structure and motion. dark matter might be detected through its effect on neutrinos. Neutrinos are ghostly particles produced in vast numbers by the Sun, supernova, and other cosmic events. They barely interact with ordinary matter, passing through planets and stars as if they weren't there. But in some theories, neutrinos might interact ever so slightly with dark matter. If this is true, scientists might be able to detect dark matter indirectly by observing changes in neutrino behavior. For example, neutrinos passing through regions of dense dark matter might scatter or change their properties in subtle ways. Detectors like IceCube, buried deep in the Antarctic ice, search for unusual neutrino signals that could hint at dark matter interactions. The chances of success are slim, but the potential payoff is enormous. Finding even a single clear signal would revolutionize our understanding of both neutrinos and dark matter, two of the universe's most elusive inhabitants. Dark matter could be warm instead of cold. Not all dark matter has to move slowly. While most theories focus on cold dark matter, particles that move relatively slowly compared to the speed of light, there's another possibility: warm dark matter. These particles would be lighter and faster, zipping through space at higher velocities. The difference might seem subtle, but it has profound effects on how structures form. Cold dark matter allows small structures to form first, which then merge into larger ones. Warm dark matter would suppress the formation of small structures, leading to a universe with fewer dwarf galaxies and a smoother distribution on small scales. Observations are still trying to determine which model fits reality better. Some discrepancies between simulations and observations have led scientists to consider warm dark matter as a possibility. The universe might be telling us that dark matter isn't quite as cold as we thought, that it has a bit more energy, a bit more motion, moving through the cosmos with a gentle warmth. The first evidence for dark matter came from galaxy rotation. In the 1970s, astronomer Vera Rubin and her colleagues made observations that would change our understanding of the universe. They measured the rotation speeds of stars in spiral galaxies, expecting to find that stars farther from the center moved more slowly, just as planets do in our solar system. Instead, they found something shocking. The rotation speed stayed constant, even at the outer edges of galaxies. This flat rotation curve meant there had to be far more mass than what we could see. Rubin's meticulous work provided some of the strongest evidence for dark matter. Her observations couldn't be explained by visible stars, gas, or dust. Something invisible was out there, dominating the mass of galaxies. For decades, her work was underappreciated, but today it's recognized as foundational. Vera Rubin showed us that the universe is more than meets the eye, and her legacy lives on in every dark matter experiment. Dark matter doesn't scatter light like fog or dust. When light passes through fog or dust, it scatters. The beam spreads out, dims, and changes direction. This scattering happens because photons collide with the particles in the fog. Dark matter doesn't do this. Light passes through dark matter completely unaffected, as if it weren't there at all. The only way dark matter influences light is through its gravitational field, which bends the path of light through curved space. This bending, gravitational lensing, is subtle and depends on the mass of the dark matter, not on any physical interaction with the photons themselves. This behavior tells us something crucial about dark matter's nature. It has no electromagnetic interaction. It doesn't absorb, emit, or scatter light in any way. It's not just invisible because it's faint or distant. It's invisible because it fundamentally doesn't interact with the light that fills our universe. Some dwarf galaxies are almost entirely made of dark matter. Most galaxies contain a mix of ordinary matter and dark matter, with dark matter usually dominating by mass. But some small galaxies, called dwarf spheroidals, take this to an extreme. These dim, diffuse galaxies contain very few stars and almost no gas, yet their stars move surprisingly fast. This indicates they're embedded in massive dark matter halos. In some cases, dark matter makes up more than 99% of the galaxy's total mass. These galaxies are almost pure dark matter, with just a sprinkling of stars to mark their presence. They orbit larger galaxies like the Milky Way as satellites, barely visible but gravitationally significant. Studying these dark matter-dominated galaxies gives scientists a clearer view of how dark matter behaves, since there's so little ordinary matter to complicate the picture. They're like laboratories for dark matter, quiet and unassuming, but full of secrets. Dark matter may be responsible for the Milky Way's warp. If you could see the Milky Way from the side, you'd notice something odd. The disk isn't perfectly flat. It's warped, with the outer edges bending up on one side and down on the other, like the brim of a hat that's been twisted. This warp has puzzled astronomers for decades. What causes it? One possibility is the gravitational influence of the Milky Way's dark matter halo. If the halo isn't perfectly spherical, or if it's been disturbed by a passing dwarf galaxy, it could pull on the outer disk, creating the warp. Another theory suggests that the Magellanic Clouds, two small companion galaxies, are tugging on the Milky Way's dark matter, and that tug is transmitted to the disk. Whatever the cause, dark matter is likely involved. It's the invisible hand shaping the visible structure, a quiet sculptor working on the grandest scales. Dark matter forms halos within halos. The universe is structured like a nested set of Russian dolls. Large dark matter halos contain smaller ones, which contain even smaller ones. This hierarchical structure emerges naturally from the way gravity works. Small clumps of dark matter form first, then merge over time to create larger structures. Some smaller halos survive the mergers, orbiting within the larger halo like satellites. Our Milky Way, for example, has dozens of smaller dark matter halos orbiting it, each containing a dwarf galaxy or cluster of stars. These subhalos can persist for billions of years, even as they're gradually torn apart by tidal forces. The result is a complex, layered structure. Dark matter isn't just a smooth halo around a galaxy. It's filled with substructure, clumps within clumps, a fractal pattern woven by gravity and time. Scientists simulate the universe to understand dark matter. One of the most powerful tools for studying dark matter is the computer simulation. Scientists input the laws of physics, the amount of dark matter and ordinary matter, and the initial conditions of the early universe. Then they let the simulation run, watching billions of years of cosmic evolution unfold in hours or days of computer time. These simulations reproduce the large-scale structure of the universe remarkably well. The cosmic web, galaxy clusters, and dark matter halos. They allow scientists to test different dark matter models, tweaking the properties of the particles to see which version best matches observations. Some simulations zoom in on individual galaxies, tracking how dark matter and ordinary matter interact over time. Others span the entire observable universe, showing how structure grows on the largest scales. These virtual universes are windows into the invisible, revealing the hidden architecture of dark matter. Dark matter might not exist at all. It's worth considering a radical possibility. What if dark matter doesn't exist? What if, instead, our understanding of gravity is incomplete? This idea, called modified Newtonian dynamics or MOND, suggests that gravity behaves differently on large scales than we expect. Perhaps the force of gravity doesn't fall off as quickly as Newton and Einstein predicted. If so, galaxies could hold together without needing extra invisible mass. MOND has had some successes. It can explain galaxy rotation curves quite well, but it struggles with other observations like gravitational lensing, the cosmic microwave background, and galaxy clusters. Most scientists favor dark matter because it explains a wider range of phenomena. Still, MOND reminds us to stay humble. Our theories are models, not reality. And sometimes, the universe surprises us in ways we never expected. Dark matter might interact through a fifth force. We know of four fundamental forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. But what if there's a fifth? Some theories propose that dark matter interacts through a new, undiscovered force that doesn't affect ordinary matter. This force could be very weak or only operate over short distances, making it hard to detect. If such a force exists, it could allow dark matter particles to interact with each other in subtle ways, affecting how dark matter clumps and moves. This might explain some discrepancies between simulations and observations. The fifth force would be invisible to us, just like dark matter itself, but it would leave fingerprints in the distribution of galaxies and the behavior of dark matter halos. Searching for signs of this force is like looking for shadows within shadows, a mystery nested inside another mystery. Dark matter could help us find alien civilizations. This might sound far-fetched, but some scientists have speculated that advanced alien civilizations could harness dark matter as an energy source. If dark matter particles can annihilate or decay, they release energy. A sufficiently advanced civilization might build structures to capture and use this energy, creating dark matter power plants. These structures might emit unusual signals, gamma rays, or other particles that don't match natural sources. Searching for these signals could be a new way to look for intelligent life. It's a long shot, and there's no evidence yet, but it's a reminder that dark matter isn't just a cosmological curiosity. It might have practical applications, uses we haven't imagined yet, and somewhere in the universe, someone else might already know how to use it. Dark matter was crucial during the cosmic dark ages after the Big Bang. The universe went through a period called the cosmic dark ages. This was a time lasting hundreds of millions of years when no stars had yet formed. The universe was filled with neutral hydrogen gas, dark and cold. But it wasn't empty. Dark matter was there, silently collapsing into the first halos, creating gravitational wells where gas could gather. These dark matter halos were the nurseries of the first stars and galaxies. Without them, the dark ages would have lasted much longer, perhaps indefinitely. Dark matter broke the silence. It provided the structure, the framework, the cradles where light would eventually ignite. When the first stars finally formed, they did so within dark matter halos. And when their light burst forth, ending the Dark Ages, it illuminated a universe already shaped by the invisible. Some dark matter might be fuzzy. Most models of dark matter assume it's made of particles, discrete little bullets flying through space. But what if dark matter is more like a wave? In fuzzy dark matter models, the particles are so light that their quantum wavelength is enormous, stretching across thousands of light years. At these scales, dark matter behaves less like particles and more like a fuzzy quantum field, a kind of cosmic mist. This fuzziness could affect how dark matter clumps on small scales, potentially resolving some tensions between simulations and observations. Fuzzy dark matter would create smoother distributions in the centers of galaxies and suppress the formation of the smallest dark matter halos. The universe, in this view, is not just made of particles and waves, but of something in between, a quantum haze that fills space and gently shapes the structures we see. Dark matter might leave traces in ancient rocks. Some scientists have proposed a creative way to search for dark matter. Look at rocks. If dark matter particles occasionally collide with atomic nuclei, they could leave microscopic damage in minerals, creating tiny tracks or defects. Over millions of years, these traces could accumulate in ancient rocks, providing a geological record of dark matter interactions. Researchers have searched for these signatures in meteorites and deep earth minerals, looking for patterns that can't be explained by cosmic rays or natural radioactivity. So far, nothing definitive has been found, but the idea is elegant. The Earth itself becomes a detector, recording the passage of dark matter over eons. If we learn to read the stones correctly, they might tell us stories about the invisible particles that have been flowing through our planet since it formed. The cosmic microwave background reveals dark matter's fingerprints. The cosmic microwave background, the faint glow left over from the Big Bang, is one of the most important tools for studying dark matter. When this light was released, about 380,000 years after the Big Bang, dark matter had already begun to shape the universe. Its gravity influenced how ordinary matter was distributed, creating patterns of density that left imprints in the cosmic microwave background. These imprints appear as tiny temperature fluctuations, hot and cold spots in the ancient light. By analyzing these patterns, scientists can measure how much dark matter existed in the early universe, how it was distributed, and how it influenced the formation of structure. The cosmic microwave background is a snapshot of the infant universe, and in that snapshot, dark matter's presence is written clearly, a silent signature in the oldest light we can see. Dark matter might form exotic bound states, just as ordinary matter can form atoms, molecules, and complex structures. Dark matter might do the same. If dark matter particles interact with each other, even weakly, they could bind together into larger structures. Some theories propose dark matter atoms, with dark electrons orbiting dark nuclei. Others suggest dark matter could form molecules or even more complex arrangements. These bound states would behave differently from isolated dark matter particles. They might clump more readily, change how dark matter halos form, or even emit faint signals we could detect. The idea is speculative, but it opens up fascinating possibilities. Dark matter might not be a simple sea of identical particles. It might have its own chemistry, its own complexity, an invisible periodic table existing alongside our own. Dark matter's distribution affects galaxy mergers. When two galaxies collide and merge, dark matter plays a crucial role in how the process unfolds. The dark matter halos encounter each other first, interpenetrating and mixing. Because dark matter doesn't collide in the usual sense, the halos pass through each other initially, then slowly fall back together due to gravity. This creates a complicated dance. The visible parts of the galaxies, stars and gas follow different paths, influenced by the evolving dark matter distribution. Over time, the dark matter halos merge completely, forming a larger, more massive halo. This merged halo provides the gravitational well for the new galaxy that forms from the collision. Understanding this process helps scientists predict what will happen when the Milky Way and Andromeda eventually merge. Billions of years from now, dark matter choreographs the dance. Dark matter experiments must be incredibly sensitive. Detecting dark matter directly requires instruments of extraordinary sensitivity. The expected interaction rate is so low. Perhaps one event per year per kilogram of detector material, that even the tiniest background noise can overwhelm the signal. That's why dark matter detectors are placed deep underground, shielded by kilometers of rock to block cosmic rays. The detectors themselves are built from ultra-pure materials, cooled to temperatures near absolute zero, and surrounded by layers of shielding. Even the people working on the experiments must be careful. Natural radioactivity in their bodies could create false signals. Despite these precautions, detecting dark matter remains incredibly difficult. The particles are so elusive that even the most sensitive instruments can only hope to catch a whisper. But that whisper, if it comes, would be worth the wait. Dark matter might cluster around black holes. Black holes are the densest objects in the universe, and their intense gravity might attract and trap dark matter. Over time, dark matter particles orbiting the black hole could lose energy and spiral inward, accumulating in a dense cloud around the event horizon. This dark matter halo around the black hole could be incredibly concentrated, far denser than dark matter anywhere else in the galaxy. If dark matter particles annihilate, this dense region would be a hotspot for annihilation signals. Astronomers have searched for excess radiation from the centers of galaxies, where supermassive black holes reside, looking for signs of dark matter annihilation. The results have been tantalizing, but inconclusive. Still, black holes remain promising places to look for dark matter's hidden glow, regions where the invisible might finally reveal itself. Dark matter helped determine the universe's geometry. One of the great questions in cosmology is, what is the shape of the universe? Is it flat, curved like a sphere, or curved like a saddle? The answer depends on the total amount of mass and energy in the universe. Dark matter contributes significantly to this total, and measurements of the cosmic microwave background have allowed scientists to determine the universe's geometry with remarkable precision. The answer: the universe is flat, or very close to it. This flatness is a delicate balance. Too much matter, and the universe would curve back on itself. Too little, and it would curve the other way. Dark matter provides much of the mass needed to achieve this balance. In this sense, dark matter doesn't just shape galaxies and clusters, it shapes the very geometry of space itself. Dark matter might decay into lighter particles, If dark matter is unstable, it could slowly decay over time, transforming into lighter particles. This process would be incredibly slow, taking far longer than the current age of the universe for most dark matter to decay. But even a tiny decay rate could produce detectable signals. The decay products might include photons, neutrinos, or other particles we could observe. Astronomers have searched for excess X-rays or gamma rays from galaxies and clusters, signals that could indicate dark matter decay. A few anomalies have been found, unexplained emissions that don't match known sources, but none have been confirmed as dark matter. If dark matter does decay, it would mean the universe is slowly changing, the invisible scaffolding gradually transforming into something else. A cosmic metamorphosis happening over trillions of years. The missing satellites problem challenges dark matter theory. Computer simulations of galaxy formation predict that large galaxies like the Milky Way should have hundreds or even thousands of small satellite galaxies orbiting around them. But when astronomers count the satellites, they find far fewer, only a few dozen. This discrepancy is called the missing satellites problem. Where are all the predicted dwarf galaxies? Some might be too faint to detect, their stars so sparse they're invisible in surveys. Others might have been destroyed by tidal forces. Another possibility is that dark matter behaves differently on small scales than we thought, perhaps interacting in ways that suppress the formation of small halos. The missing satellites problem is one of several small-scale challenges facing cold dark matter models. It doesn't disprove dark matter, but it suggests we might not fully understand how it works. Dark matter might be asymmetric like ordinary matter. In the ordinary world, matter vastly outnumbers antimatter. This asymmetry is one of the great mysteries of physics. Why is there more matter than antimatter? Some theories propose that dark matter might have a similar asymmetry. Perhaps in the early universe, processes created slightly more dark matter particles than dark antiparticles, just as happened with ordinary matter. This asymmetric dark matter would mean that dark matter particles don't annihilate easily today, since there are no dark antiparticles to annihilate with. This changes how we search for dark matter. Instead of looking for annihilation signals, we'd focus on direct detection, catching dark matter particles as they pass through detectors. Asymmetric dark matter also offers a potential explanation for why the amount of dark matter in the universe is roughly 5 times the amount of ordinary matter. The two asymmetries might be linked, shaped by the same processes in the early universe. Dark matter could affect the evolution of life. This is a speculative idea, but an intriguing one. If dark matter particles occasionally collide with atomic nuclei, they could potentially cause mutations in DNA. Over geological timescales, this could contribute to genetic variation and evolution. The effect would be incredibly small, far less than natural radiation sources like cosmic rays or radioactive elements. But some scientists have wondered whether fluctuations in dark matter density, as the solar system moves through different regions of the galaxy, could correlate with changes in mutation rates or mass extinctions. There's no solid evidence for this yet, and most researchers are skeptical. Still, it's a reminder that dark matter isn't just out there in distant galaxies. It's here now, flowing through everything, including the cells of every living thing on Earth. Some dark matter theories predict it clumps into dense nuggets, while most dark matter models describe smooth, diffuse halos. Some theories predict that dark matter could form incredibly dense clumps called dark matter nuggets or macros. These objects could be much heavier than ordinary atoms, perhaps as heavy as asteroids or small moons, but still microscopic in size. They'd be like ultra-dense dark matter hailstones drifting through space. If these nuggets exist, they might occasionally pass through the Earth or other planets, potentially creating detectable signals. They could leave tracks in sensitive detectors or cause tiny seismic events. Searches for these objects have so far come up empty, but they represent yet another possibility in the wide spectrum of dark matter theories. The invisible universe might not be smooth at all. It might be grainy, lumpy, filled with invisible stones too small to see, but massive enough to matter. Dark matter doesn't cool down like ordinary matter. When ordinary matter loses energy, it radiates heat and light, cooling down over time. This process allows gas clouds to collapse into stars and planets, shedding energy until they reach a stable configuration. Dark matter can't do this. It has no way to radiate energy, so it can't cool down. When dark matter particles fall into a gravitational well, they speed up, gaining kinetic energy. But without a way to shed that energy, they remain in motion, forming extended puffy halos rather than compact objects. This fundamental difference between dark matter and ordinary matter is why the universe has the structure it does. Dark matter provides the scaffolding, diffuse and extended, while ordinary matter fills in the details, condensing into bright, compact structures. The two work together, each playing a role the other cannot. Dark matter might be responsible for unexplained cosmic rays. Cosmic rays are high-energy particles, mostly protons and atomic nuclei, that constantly bombard Earth from space. Most come from supernova explosions and other violent astrophysical events, but some cosmic rays have energies that are difficult to explain. Where do they come from? One possibility is dark matter. If dark matter particles annihilate or decay, they could produce high-energy particles that eventually reach us as cosmic rays. Researchers have searched for unusual features in the cosmic ray spectrum, looking for signals that don't match conventional sources. A few anomalies have been found, including an excess of positrons, the antimatter counterpart of electrons. Could this be dark matter? It's possible, but other explanations exist too. The mystery remains unsolved, a puzzle written in the particles that rain down from the sky. Dark matter forms a galactic fountain in the Milky Way. Within the Milky Way, dark matter isn't static. It flows and circulates, influenced by the galaxy's rotation and the gravitational pull of its visible matter. Some simulations suggest that dark matter follows a fountain-like pattern, streaming into the galaxy along certain paths and flowing out along others. This circulation mixes dark matter from different regions, creating a dynamic, ever-changing distribution. The Sun and Earth move through this flowing dark matter, and the density we experience might vary over time as we pass through different streams and currents. Understanding this galactic dark matter fountain helps refine our expectations for direct detection experiments. The signal we're looking for might not be constant. It might ebb and flow with the rhythms of the galaxy itself. Dark matter might solve the too big to fail problem. Computer simulations predict that the largest satellite galaxies of the Milky Way should be extremely dense, packed with dark matter. But observations show they're much less dense than predicted. This is called the too big to fail problem. These satellites are massive enough that they shouldn't have failed to accumulate more dark matter, yet they did. Why? One possibility is that dark matter interacts with itself in ways we haven't accounted for. These interactions could transfer energy and reduce the density of dark matter in the centers of small galaxies. Another idea involves the effects of ordinary matter. When stars form and explode as supernova, they can push gas around, and this might also affect the dark matter distribution. Solving the too big to fail problem could reveal new properties of dark matter or teach us more about how ordinary and dark matter influence each other. Dark matter experiments span the globe. The search for dark matter is a global effort. Experiments are operating or planned in locations around the world, from mines in South Dakota to laboratories in Italy, from underground facilities in China to detectors in Antarctica. Each experiment uses different techniques and targets different types of dark matter candidates. Some look for direct collisions between dark matter and ordinary matter. Others search for the products of dark matter annihilation or decay. Still, others try to produce dark matter particles in accelerators, smashing ordinary matter together at high energies. The diversity of approaches reflects our uncertainty about what dark matter is. We're casting a wide net, hoping that somewhere, one of these experiments will finally catch a glimpse of the invisible. And when that happens, scientists around the world will be ready to listen. Dark matter might form dark disks within galaxies, while most of the Milky Way's dark matter is in a roughly spherical halo. Some theories suggest that a small fraction might have settled into a thin disk, just like the disk of stars and gas. If dark matter can interact with itself, even weakly, it could lose energy and collapse into a more flattened configuration. This dark disk would co-rotate with the visible disk, and the sun might be moving through it right now. The presence of a dark disk would change the expected signals in dark matter detectors, increasing the detection rate and altering the distribution of recoil energies. Some researchers have looked for evidence of a dark disk in the motions of stars, but the results are inconclusive. The idea remains speculative, a tantalizing possibility that adds another layer of complexity to the dark matter puzzle. Dark matter affects the sound waves in the early universe. In the first few 100,000 years after the Big Bang, the universe was filled with a hot plasma of ordinary matter and radiation. Sound waves, pressure oscillations, rippled through this plasma, creating regions of higher and lower density. These baryon acoustic oscillations left an imprint on the distribution of matter that we can still see today in galaxy surveys. Dark matter played a crucial role in shaping these sound waves. Its gravity amplified the density variations, helping them grow into the structures we see now. By studying the pattern of galaxies on large scales, astronomers can measure the characteristic scale of these ancient sound waves. This measurement, in turn, tells us about the amount and properties of dark matter in the early universe. The echoes of creation still ring through space, and dark matter shapes their song. Dark matter might be detected through its effect on stellar evolution, Stars are incredibly sensitive to their environment. Even tiny changes in temperature, composition, or surrounding matter can affect how they evolve. Some scientists have proposed that dark matter accumulating inside stars could alter their structure and lifespan. If dark matter particles are captured by a star's gravity and sink to its core, they might annihilate, releasing energy. This extra energy source could change how the star burns, potentially extending its life or altering its brightness. Astronomers have searched for unusual stars whose properties might indicate the presence of dark matter, looking in regions where dark matter is expected to be dense, like the center of the galaxy or the cores of globular clusters. So far, no definitive dark matter signal has been found in stellar observations, but the search continues, star by star. Dark matter might cluster along cosmic strings. Cosmic strings are hypothetical defects in the fabric of space-time, one-dimensional remnants from the early universe. If they exist, they would be incredibly thin, but incredibly massive, stretching across vast cosmic distances. Some theories suggest that dark matter might cluster along these strings, attracted by their intense gravitational fields. The result would be filaments of dark matter far denser than typical halos, potentially creating strong gravitational lensing effects or enhanced annihilation signals. Finding cosmic strings, if they exist, is challenging enough. Finding dark matter concentrated along them would be even more difficult. But the idea illustrates how exotic the universe's structure might be. Dark matter doesn't just fill space uniformly. It responds to every gravitational influence, gathering in patterns and concentrations that reflect the hidden architecture of the cosmos. The search for dark matter has driven technological innovation. Looking for dark matter has pushed the boundaries of technology. Detectors must be so sensitive they can register the tiny recoil of a single atomic nucleus bumped by a dark matter particle. This requires advances in cryogenics, materials science, electronics, and shielding techniques. The same technologies developed for dark matter searches have found applications elsewhere, in medical imaging, quantum computing, national security, and fundamental physics. The quest to understand the invisible has created tools and methods that benefit many fields. In this way, dark matter research, even if it hasn't yet found its target, has already paid dividends. The search itself teaches us, challenges us, and drives us to build better instruments for peering into the unknown. Dark matter might be made of multiple types of particles. We often talk about dark matter as if it's a single substance, but there's no reason it has to be. Just as ordinary matter includes many different particles, electrons, protons, neutrons, neutrinos, and more, dark matter could be a mix of different components. There might be heavy dark matter particles, light dark matter particles, and maybe even dark radiation. Each type could have different properties and play different roles in the universe's structure. Some might clump tightly in galaxy centers, while others remain diffuse. This multi-component dark matter could help resolve some of the discrepancies between simulations and observations. It would also make the universe richer, more complex, and more difficult to understand. But that complexity might be closer to the truth than any simple model. Dark matter experiments sometimes find unexpected things. The search for dark matter is so difficult that it requires extraordinary sensitivity and precision. These same qualities make dark matter detectors excellent tools for discovering other rare phenomena. Over the years, dark matter experiments have detected things they weren't looking for: rare radioactive decays, solar neutrinos, and even signals that led to better understanding of detector backgrounds. In one case, a dark matter experiment placed strict limits on exotic particles called solar axions. In another, the techniques developed for dark matter searches were adapted to study neutrinos from distant supernova. The hunt for the invisible often reveals the unexpected, and even if dark matter remains elusive, the journey teaches us about the universe in ways we never anticipated. Dark matter might leave gaps in gravitational waves. When two black holes merge, they send ripples through space-time called gravitational waves. These waves carry information about the masses and spins of the black holes. But some theories suggest that if dark matter is present in large amounts near the black holes, it could affect the gravitational wave signal, creating subtle distortions or gaps. By carefully analyzing the signals detected by observatories like LIGO and Virgo, scientists might be able to infer the presence of dark matter near merging black holes. This would be an entirely new way to study dark matter, using gravity waves instead of light or particles. The technique is still in its infancy, and the effects, if they exist, will be incredibly subtle. But in the future, gravitational wave astronomy might open yet another window into the invisible universe. Dark matter could be hiding in plain sight. One of the strangest possibilities is that dark matter might not be exotic at all. It could be something mundane, just very hard to see. Some astronomers have suggested that dark matter might be composed of ordinary matter in forms that don't shine. Brown dwarfs, rogue planets, black holes, neutron stars, or even cold white dwarfs. These objects, collectively called MACOs, massive compact halo objects, would be invisible or nearly so, but still have mass and exert gravity. Extensive searches for MACOs have been conducted, looking for gravitational lensing events when these objects pass in front of distant stars. The results largely ruled out MACOs as the dominant form of dark matter. There simply aren't enough of them. But the idea reminds us that not every mystery requires an exotic explanation. Sometimes the answer is simpler than we think, just hidden in a different way. Dark matter might influence the expansion rate of the universe. The expansion of the universe is accelerating, driven by dark energy. But dark matter also plays a role, though a different one. Dark matter's gravity slows the expansion, pulling on galaxies and clusters, resisting the outward push of dark energy. The balance between these two forces determines the universe's ultimate fate. If dark matter were more abundant, it might slow or even reverse the expansion, leading to a big crunch. If it were less abundant, the acceleration would be even more pronounced. By measuring the expansion rate precisely, astronomers can learn about both dark matter and dark energy. These measurements involve observing distant supernova, the cosmic microwave background, and the distribution of galaxies. Each observation adds a piece to the puzzle, helping us understand the invisible forces shaping the cosmos. Some dark matter could have evaporated into dark radiation. In the early universe, when temperatures were incredibly high, dark matter might have existed in different forms. Some theories propose that dark matter was once much more abundant, but as the universe cooled, a portion of it decayed or transformed into dark radiation, a relativistic form of energy that behaves more like light than matter. This dark radiation would still be present today, contributing to the total energy of the universe, but not to its mass. It would affect the expansion rate and the formation of structure in subtle ways. Observations of the cosmic microwave background and large-scale structure have placed limits on how much dark radiation could exist, but they haven't ruled it out entirely. The invisible universe might be even more varied than we imagined, filled not just with dark matter, but with dark light as well. Dark matter research brings together many fields of science. The study of dark matter is truly interdisciplinary. It involves astrophysicists observing galaxies and clusters, particle physicists designing detectors and theories, cosmologists studying the early universe, computer scientists running massive simulations, and engineers building the sensitive instruments needed for detection. Chemists work on purifying materials. Geologists help identify underground sites for detectors, and statisticians analyze the data to separate signal from noise. This collaboration across disciplines is one of the great strengths of dark matter research. No single field has all the answers, but together they create a more complete picture. The search for the invisible draws on the collective knowledge of humanity, bringing together minds from around the world to solve one of the universe's deepest mysteries. Dark matter might help explain the Fermi paradox. The Fermi paradox asks a troubling question. If the universe is so vast and old, where are all the aliens? Why haven't we seen any signs of intelligent life? One speculative answer involves dark matter. If dark matter can be harnessed as an energy source or used for propulsion, advanced civilizations might prefer to live in regions of space where dark matter is dense, places far from stars and galaxies. They might even build structures that are invisible to our telescopes, using dark matter in ways we can't detect. Or perhaps dark matter itself is hazardous in ways we don't understand, limiting where life can survive. These ideas are highly speculative, bordering on science fiction, but they illustrate how dark matter might play unexpected roles in the universe's story. Even the question of whether we're alone might somehow touch the invisible.